Hello, and welcome to the video lecture accompanying Chapter 10 on the topic of projectile and satellite motion from Conceptual Physics 12th edition by Hewitt. Okay, so in this 10th chapter, we're going to kind of cover the last of the chapters that cover the basics of motion. Then we're going to kind of move on to discussing states of matter and then ultimately thermodynamics, the physical study of heat. All right, well, let's finish up motion then. So this is a fun chapter because we're going to get to tell a story. We're going to move from talking about projectiles, think launching a cannon or something, into satellite orbits. So how does one lead to the other? All right, well, let's see. So projectile motion. All right, now we've looked at projectile motion already. We've discussed it in terms of the velocity, when we discussed the velocity vector, when we talked about the really just defining the kinematics of acceleration and velocity. So we've kind of have discussed it already, but here we're going to get into it a bit more. So without gravity, a tossed object follows a straight line path. So in space, for example, you throw something, it just continues in that line forever. There's no force to act on that object. With gravity, however, the same object tossed at an angle follows a curved path. All right, because gravity is going to act in one direction only, and it's going to mean that it's constantly changing that velocity vector. So that means that the definition of a projectile is any object that moves through the air or space under the influence of gravity. All right, continuing in motion by its own inertia. So that's the idea. So rockets would not be a projectile because they continue in motion with more than their own inertia. They have thrust. Anything that is not in a gravitational field, so objects that are in deep space, would not be a projectile because there's no gravity to act on them. All right, but definitely, things like launching a cannonball, throwing a ball, tossing a rock off the side of a cliff or something, or into a lake, those are all examples of projectiles. All right, and they take that characteristic curved path, which we're going to see. All right, so a really neat thing and an important way to understand projectile motion, and honestly an easy way to understand it, is that it's a combination of horizontal motion, or a horizontal component, and vertical motion, a vertical component. And that's all it is just taking those two types of motion and putting them together. So both of these motions, if you were to look at them without looking at the other, would be totally independent. So in other words, what's happening in the horizontal direction does not affect what's happening in the vertical direction, and likewise, they just don't affect each other. There's no cross influence between vertical motion and horizontal motion. And furthermore, the horizontal motion of projectiles is constant, just like this green dot moving across the ground. The distance between any two segments, assuming that they're all measured at equal times, is always the same. So in other words, the green dot moves the same amount of distance in the same amount of time, unchanging. But of course, in the vertical direction, it's totally a different story because it's free fall. All right, now we've seen free fall before when we talked about acceleration. And that's what a projectile is in the vertical. It is precisely, unequivocally free fall. And free fall has, small displacements at first, and then as gravitational acceleration grows the velocity vector, each subsequent displacement becomes larger and larger. That's the very nature of free fall. Okay? So all we do is just put those two types of motions together. Projectiles launched horizontally, all right, is an example, one particular type of projectile. That when we think about a projectile launched horizontally, the horizontal component of velocity doesn't change, and we are assuming that air drag is negligible. The ball travels the same horizontal distance in equal times, as I said, okay, because there's no component of gravitational force that acts horizontally. Gravity only acts straight down, right? Like in this picture, gravity would only act straight down. So the horizontal motion must remain constant, all right? So here's the idea. Here is what's happening in the horizontal direction. Here's what's happening in the vertical. Now, would either of these things really happen? Well, figure one would happen if there was no gravity, right? Like if this was on a space station. The ball would just continue off the edge of the table and just keep coasting along, floating along. If you've seen videos of objects in the International Space Station, that's what they do, right? On the other hand, if you just drop something straight down, in other words, gave it no initial horizontal velocity, it would just fall straight down like picture number 2. But when we put them together, when we combine them, we get actual projectile motion right here. And then this last little diagram here, this last figure, really shows you that this combination does match up. If I draw vertical lines to connect the dots, and I draw horizontal lines to connect the dots, I can find that my position in 2D space is truly a combination of constant velocity horizontal motion and constant acceleration vertical motion, giving me this, right? And that's all a projectile is, okay? So conceptually, I think that's fairly simple, right? All right, so the curvature of the path is a combination of the horizontal and vertical components of motion. You can totally handle them separately, all right? Now, when you launch something at an angle, that would be like this picture here too with the cannon, right? When you launch something at an angle, then you get this particular parabolic path through the air. Now, the reason this one that didn't look parabolic by launching the ball off the edge of the table is, first of all, maybe it did because it is half a parabola, but it wasn't a full parabola because we started the object with entirely horizontal velocity, no vertical component. But when you launch something at an angle, the initial velocity, this would be v naught, would be the hypotenuse here, is a combination of the vertical and the horizontal initial velocities. Okay, and together they make a right triangle, as we can see, okay, or a parallelogram, okay? And so that's the idea, is that any object that has both non-zero initial vertical and initial horizontal velocities will take a parabolic path. And notice at the top of the path, the vertical component of the velocity, the instantaneous vertical component of the velocity is 0, because it's just like tossing something straight up. At the top, it's momentarily at rest in the vertical direction. But the projectile is not momentarily at rest in its entirety because it's still coasting along in the horizontal. And this, of course, is assuming negligible drag, which actually is a pretty good assumption for large objects, because then the inertia is so much bigger than the drag force that it's not going to be super noticeable. Unless it's a large object that has a lot of surface area, right? But if it's a large, dense object, you should be fine, okay? Think something maybe that's like streamlined, you know, like a torpedo or something. So the curved path of a projectile that undergoes acceleration only in the vertical direction, because again, this is the direction of acceleration, while moving at constant horizontal speed. This is the parabolic path, okay? And notice that the final velocity, when the object crashes back into the ground, assuming that the ground is level, is exactly the same magnitude as the initial velocity. This vector is the same length, okay? And its components are the same lengths as well. It's just flipped upside down, all right? So projectiles launched at an angle, the paths of stones thrown in the angle upward and downwards, all right? So vertical and horizontal components are independent of each other, right? So check out the two different paths. It's pretty cool. This is just doing the same sort of thing, but here's an object that's given an initial horizontal velocity. That's this path here, and this is one that's actually kind of tossed downwards, right? And you can see that actually affects the range and the angle at which the object crashes into the ground. All right. The paths of cannonballs shot up at an upward angle. The vertical distance that a stone falls is the same vertical distance it would have fallen if it had been dropped from rest and had been falling for the same amount of time. In other words, 5t squared. Okay? And we know this 5t squared from the kinematic equation that tells us that position is y naught plus v naught y times t minus 1/2 gt squared. And we're approximating g as 10 meters per second squared. So then this term becomes the term of vertical displacement, okay? And so that just tells you how far your parabola is from the path that the ball or object would have taken in the absence of gravity. So the dotted line is the space scenario, the no gravity, not on the surface of Earth scenario. And then the difference between that dotted line and reality, the parabolic path, is the same as how far the object would have fallen in free fall if you dropped it from rest off the edge of something, right? Which is remarkable, but it does make sense because it's the same physics after all. Okay? And the paths of projectiles follow a parabolic trajectory. This is just kind of repeating the same information with a very similar picture. The horizontal component along the trajectory remains unchanged. Only the vertical component changes, and velocity at any point is computed with the Pythagorean theorem, diagonal of the rectangle. Because we can independently find both this component and the vertical component. Now I'll tell you, finding the horizontal component is darn easy because it literally is just equal to the initial. So here, like Vx is just equal to V naught x. Here, same thing. Vx is just equal to V naught x. If we want to find the vertical component of velocity, Well, Vy, okay, this would be V naught y, right? So then what about here at this point? Well, we need to know either how high it's gone or how much time has passed. If I know how much time has passed, then I could find this shorter instantaneous vertical component of velocity using Vy equals V naught y minus gt, right? So if I asked, what is the speed of the projectile after it has been airborne along its parabolic trajectory for 1 second? Well, then I just plug in t equals 1, I can plug in g equals 9.8 and find the instantaneous vertical velocity, all right? And then as I said, finding the instantaneous horizontal velocity is just literally plugging it in because I'm assuming you know it. And then if you wanted to find the total, this shorter hypotenuse, and I say shorter compared to the initial velocity, the total velocity, well then you just use the Pythagorean theorem. This is what they mean. V naught x squared plus V y squared. Notice here I put V naught x just to highlight the fact that this is always just whatever value you're given. It doesn't change. But here you need to actually find Vy, usually by calculating time. All right? So there's another interesting thing about projectile motion, and that's that different horizontal distances can lead to the same range. And specifically, the same range is obtained from two different launch angles when the angles add up to 90 degrees. So objects thrown at an angle of 60 degrees have the same range as if they were thrown at an angle of 30 degrees, right? So check out the 60 and 30, right? Here's the 30 degree angle, and this is the angle above the horizontal, and that's the resulting range. And then at 60, it goes much higher. It spends more time in the air. It does indeed spend more time in the air, but its horizontal range, assuming level ground, so hitting the ground at the same height it started at, is equal to if you launched at 30, right? So as long as they add up to 90 degrees, you'll always get the same, right? And even the extreme examples of 0 degrees and 90 degrees give you the same range. They both give you 0. If you shot something at 0 degrees, it's already on the ground, so it doesn't actually spend any time in the air. And if you shot something at 90 degrees, it just goes straight up and straight down, so it never actually covers any horizontal distance. All right? You could do 75 and 15. And then what about 45? Well, 45 is a special one because in that sense, it's unique. You can't, there's nothing you can add to 45 to sum up to 90 other than 45. But 45 is also the maximum range. Right? 45 degrees is maximum range. And range, again, is just the horizontal distance the object travels before crashing back into the ground. Okay? And so, yeah, that is the angle, and it can be proved mathematically that 45 degrees is the greatest range. Okay? So different horizontal distances. So the maximum range occurs for the ideal launch at 45 degrees. Ideal because that's without air resistance. With air resistance, it's actually going to be less than 45 because you want it to. Because if you think about it, with air resistance, the 60 degrees has more time to get buffeted by the air. The 30 degrees is less time to get buffeted by the air because its actual path length is less. And so when you actually have air resistance, your maximum range is going to be achieved at angles less than 45 every time. All right. So with air resistance, maybe 25 to 34, and let's see. So with air resistance, the maximum occurs for a baseball, okay, and for a golf ball about 38. So it kind of depends how sleek the object is. The golf ball is able to get a maximum range closer to 45 because golf balls have very little drag. That's actually a big story about the dimples of the golf ball. Is it really reduces the drag of the ball. In general, spherical objects are fairly high drag objects. If we really want to have low drag objects, we need things like arrows or like streamlined objects that are long and sleek. But as far as balls go, having dimples significantly reduces the drag effects, especially at the size and velocities of golf balls. All right. So projectile motion. Without air resistance, the time for a projectile to reach maximum height is the same as for the time for it to return to its initial level. There's total symmetry in the parabola. This, if we were to cut it right down the middle, the time to get to the top is the same as the time to get from the top to the bottom. Now we know that when air resistance, that changes. And the change is the same as it is with free fall. If air resistance is introduced, then the time to get back down is greater than the time to get up. And there's, the key reason for that is the average velocity will be less on the way down than on the way up if drag is acting the whole time, if air resistance is being applied the whole time. Okay, so the velocity of a typical projectile can be represented by horizontal and vertical components. Assuming negligible air resistance, so an ideal projectile, the horizontal component along the path of the projectile does what? Okay, So it's a good thing to make sure that, that the ideas are sinking in, they're making sense. Not meant to be a difficult question. Make sure you can answer it. Okay, so the answer is, of course, C, remains the same. There's no force horizontally, thus there can be no acceleration, which means the velocity must remain constant. Okay, and that's because of Newton's second law, F equals ma. All right, if F is 0, obviously m is not 0, thus acceleration must be 0, and acceleration is 0, then v, and then just becomes v naught minus at, well, then v just equals v naught. So that's the story of how we can say that no force means unchanging velocity. You can also use Newton's first law and just say, oh, well, if there's no force, then inertia says you have to remain, along the same path, okay? So, when no air resistance acts on a fast-moving baseball, its acceleration is, okay, again, look at your options, make sure you can answer this. Okay, pause if you need to. It's G, just G, and G points down, okay? No other direction, it's down, okay? So neglecting air drag, a ball tossed at an angle of 30 degrees with the horizontal will go as far downrange as one that is tossed at the same speed at an angle of, if you're paying attention, you know this one, 60, okay? Because 30 and 60 sum to 90. Yeah, that's how you can always find the other angle that achieves the same range. Satellite motion is an example of a high-speed projectile. Wait, what? Really? Satellites are high-speed projectiles? I mean, I guess, right? You shoot a satellite up on some rocket, and then it goes up into space, and then it orbits Earth, right? So we think about satellites like the International Space Station or all those communication satellites. They're up there for a long time, so they're just up there going around Earth. It's not really what you think of as a projectile, though. Projectiles tend to just go up and come right back down. Why does a satellite not come back down? How is a satellite a projectile but able to stay above Earth for years in many cases? Well, in fact it is, which is pretty cool. And let's talk about how that can be the case, okay? So a satellite is simply a projectile that falls around Earth rather than falling into it. So it falls around Earth, okay. Sufficient tangential velocity needed for orbit. With no resistance to reduce speed, a satellite goes around Earth indefinitely. Why is there no resistance? Well, because satellites are above the Earth's atmosphere. So up to this point, we've been saying, oh, negligible resistance. And satellites really have negligible resistance. Is there still molecules in space? Yeah, there's still, incredibly diffuse gas in space. There's inevitably little tiny particles of dust that are going to exist in space. I mean, some of them are, raining down on the planet all the time, but it's so minuscule compared to actually being in the atmosphere of Earth, okay? And really kind of the minimum distance above the surface of Earth that a satellite can be at in order to be out of Earth's atmosphere is about 300 kilometers. So as long as an object is 300 kilometers above the surface of Earth, it is outside of the atmosphere and it can just fall indefinitely. Okay? So let's talk about what we mean by sufficient tangential velocity. Here's an idea. As the ball leaves the girl's hand, 1 second later, it will have fallen how far? Okay? Now we're going to circle back around to satellites, but let's do a series of thought experiments with some good checks here, concept checks. Okay? So 1 second, it will have fallen how far? Well, does the picture give it away? Sure does. 5 meters below the dashed line, okay? And we know that from this formula. We know it from the negative 1/2 gt squared, okay? That tells us how far it's fallen, okay? So whatever the speed, it still falls 5, right? Because the speed that she throws it at, because these green arrows would represent 3 different horizontal tosses that she's given the ball, right? With this one being the fastest. That no matter how fast she's tossing it, it will always fall 5. That part is unchanging. Okay, so every second, any object falls 5 meters. Okay, so now let's consider the girl again. Somehow she's growing to be about 300, maybe more, actually much more, about maybe 2,000 kilometers tall, right, by the scale here. Or maybe she's on one of those really small worlds, like in The Little Prince. Okay, but regardless, this is supposed to be a planet, right? And we have our giant up here. And now she's going to toss the ball again, but she's going to toss it really fast, okay? So now the speed is great enough to ensure that its falling distance matches Earth's curvature. That falling distance is unchanged. Every single object will fall 5 meters in the first second, okay? And then in the, if you think about it, as long as the Earth has curved down 5 meters in whatever horizontal distance was covered, right? Because look, you can see the Earth's curving down here, right? So as long as that curvature matches the toss, then what happens? The ball never hits the ground. because then the next second, it's going to fall 5 meters relative to where it was before, okay? And what has the Earth done? It's curved down another 5 meters, all right? And so in that sense, it's like it's moving, and the Earth is curving away from it, so it never actually hits anything. And that's all a satellite is. It's just a very fast projectile, ouch, that never hits the ground, okay? All right, so it has that constant velocity, all right, or constant speed, but its direction is changing because it is being acted on by gravity. So the velocity vector is changing. This is still an accelerating system, but its speed is constant, all right? And its gravity doesn't change its speed. Gravity only changes its direction. So gravity is what makes that circular path possible, because after all, this is a projectile, all right? But the gravity will not affect its speed. Why not? Because gravity doesn't affect horizontal components of velocity. And the speed, when at any point, is horizontal relative to the vertical direction. But here we've zoomed out so much, the vertical direction is a bit different. The vertical direction now, y, is just an arrow that points towards the center of the Earth. Because if we were to look at any one of these points, right, the vertical is just towards the center. So now the vertical direction is more like the radius of the orbit, right? Same idea, because it is the direction that gravity acts, okay? So, positioning, a bit about satellites. Beyond Earth's atmosphere, where air resistance is almost totally absent, so space shuttles are launched to an altitude, for example, 150 kilometers, okay, more to be above the atmosphere, and then they're angled in a way and then given an initial final thrust, a final push to make them that ideal projectile, to make them that ideal projectile where they're going to follow that path with enough horizontal velocity that they never hit the ground, okay? So that their horizontal displacement is great enough that by the time they fall in that 5 meters, the Earth has also curved under them 5 meters, okay? So, satellites move in a direction perpendicular to the force of gravity acting on it, okay? Because the force of gravity acts towards the center of the planet, all right? And the instantaneous velocity of the satellite at any point is just 90 degrees to that. The period for one complete orbit about Earth for objects that are close to the Earth, so that's the ones that are at that minimum distance, which is called low Earth orbit, just that minimum distance to be above the atmosphere, so in a sufficient approximation of space, the vacuum of space. Well, they have a really incredibly short period of about 90 minutes, all right? Now, the higher the satellite, the longer the period. There are some satellites that are so high up, they're actually many times above the Earth, the surface of Earth, than Earth's own radius. Sometimes up to 6 Earth radii above Earth. So these are satellites that are really incredibly high up. They take much longer to get to, okay? But those types of satellites have much longer orbits. They can have orbits that are equal in length to the orbital rotation, or excuse me, the axial rotation of Earth of 24 hours. So it's possible to have orbits that are 24 hours. And case in point, think about the moon. The moon is so far away, it's 60 Earth radii away, that its orbital velocity, because it follows all the same rules of man-made satellites, but the moon is 60 Earth radii away, so that its orbital period is about 27 Earth days, okay? So the further away, the slower the period. And you can think about that because the further away, the weaker the gravity, okay? Here's the idea. This is how fast you have to go, right? So if you were to have a satellite that was like, say, right at the surface of Earth, it would have to travel 8,000 meters per second because that's the actual curvature of Earth. So in other words, the Earth drops 5 meters for every 8,000 horizontal meters you go, okay? Because it's a sphere, right? That's a kind of the approximate curvature of Earth. So that means that if you want to have a satellite that never hits the ground, right? If you want to turn a projectile into a satellite, you have to make sure that its velocity is 8,000 meters per second, or 8 kilometers per second, all right? Now that only applies to the very surface of Earth. Gravity is a force that becomes progressively weaker the further away you go. When you get up to heights of 300 kilometers above the surface of Earth, gravity is not that much weaker, but it is a few percentage points weaker than it is at the surface. And that means that you don't have to go quite that fast. and instead you can go about 7,000 or 7,200 or a few hundred meters per second less, and those are the satellite velocities. So when we talk about satellites being fast projectiles, we're not kidding. That is incredibly fast. I mean, if we were to put that in the context of jets, Mach is 330 meters per second. So like a Mach 5 jet is going, like these unbelievable, like prototype jets, they're only going like 1,500 meters per second, okay? That's nowhere close to satellite speeds. But of course, the jet has to actually do this through atmosphere, which is a huge hurdle, right? Whereas satellites get to do it in the vacuum of space. It's much easier to go quick when you don't have air resistance, turning a lot of that kinetic energy into heat, okay? Because once you start turning kinetic energy into heat, that's a lot of heat. That's why satellites burn up on re-entry, okay? Now, obviously, you can have these like heat shields and cause, like allow, say, astronauts to come back to the surface of Earth safely, but they have to go through that atmosphere at really high speeds, and they try to decelerate as quickly as possible and slow down once they get into the atmosphere, all right? So here's the idea. If you had like some racetrack like this and you were going around, right, and you had to like jump the gap and not hit the ground, well, you'd have to be going 8 kilometers per second. All right? That's the way to actually make the gap. So when you toss a projectile sideways, it curves as it falls. It will be an Earth satellite if the curve it makes, okay? Again, if you're paying attention, you should be able to answer this, but I want to make sure. Make sure you can answer this question, okay? Yep, it just has to match the curved surface of Earth, okay? 8 kilometers per second, right? And that's because the Earth curves 5 meters down for every 8 kilometers across, all right? When a satellite travels at a constant speed, the shape of its path is what? Okay, what's the one that gives us constant speed? Okay, we're talking about this. It's a circle. Now you might wonder, like, well, what's an ellipse? Is it an ellipse? Well, it's only an ellipse if the speed is non-constant. And elliptical orbits are entirely possible. We'll talk about them in just a minute. But the simplest case, the constant speed case, is a circle, all right? Elliptical orbits work and they follow the same ideas, but they're orbits where the speed actually varies a little bit between different points in the orbit, okay? All right, so here's an idea about circular orbits. A payload into orbit requires control over the direction of the rocket and the speed of the rocket. Initially, the rocket is fired vertically, then it's tipped. Once above the atmosphere, the rocket is aimed horizontally, right? Because otherwise it'll just kind of go up and come back down. And then it's given an initial boost, all right? A final thrust to an orbital speed of around 8 kilometers per second. And again, it's always going to be less because it's always, a few hundred kilometers above the surface. And then it's going to fall around the Earth and become an Earth satellite, all right? Whatever payload is left, and at this point it's probably dropped off. It probably it's shot up initially, probably dropped one of its extra fuel containers, and then up here after the final thrust is going to drop more kind of empty fuel canisters, large empty fuel chambers. Okay, so enough of circular orbits. Hopefully that makes sense. It's a neat, elegant, fun idea that a satellite is just a really fast projectile. And then it allows for a really fun question that I ask my students, and you can ask people as well. You can ask your friends and family. You can be like, what allows a projectile to stay in space? That's badly phrased. Let me try it again, right? So what makes a satellite? What allows a satellite to stay in space? Because some people they think because they see astronauts floating around, they see satellites, and they think, oh, maybe the key about satellites is they're far away from Earth. So they don't experience a lot of Earth gravity. The idea is that they've partially escaped Earth's gravity, hence the whole weightlessness that we see with astronauts. But then when you realize that weightlessness is actually just free fall, like in an elevator or something, or some amusement park ride, and that what's happening is that what makes a satellite go in space is just that it's going really fast. That's it. It's falling just like anything else. Just like if I, lift an object up and drop it, it falls straight down. So are satellites, they're falling straight down. The only thing that separates them is that they're moving really fast to the side. That's it, right? All right, so elliptical orbits. A projectile just above the atmosphere will follow an elliptical path if it's given a horizontal speed greater than 8 kilometers per second. So like, what if you give it too much thrust? Well, then you're going to overshoot the circle a little bit, but gravity will pull you back. but the result is going to be an elliptical path rather than a circular path. All right? So an ellipse is a specific curve. It's an oval path. So an example, a circle is a special case of an ellipse when its two foci coincide. Okay? So an ellipse is defined by its foci. All right? So the idea is it's got 2 points that define the shape of the ellipse. If the two foci are really far apart, then the ellipse is very elongated, which is called a very eccentric ellipse, or it has high eccentricity. If the two foci are very close to each other, then it starts to become a circle. And then a circle is just an ellipse that has zero eccentricity. Just like a square is a rectangle with equal sides, right? A circle is a special type of ellipse. So elliptical orbits. So the speed of a satellite varies. Initially, if the speed is greater than needed for a circular orbit, the satellite overshoots the circular path and moves away from Earth. Okay? So here's that case of it moving away from Earth, going way over there. The satellite loses speed as it does that, and then it starts to fall back towards Earth. It rejoins its original path with the same speed it had initially, and that procedure is repeated. Okay? Because again, there's no air resistance. There's symmetry between forces here. And so what happens if you overshoot, if there's too much initial thrust, or perhaps you wanted an elliptical orbit, then you're going to have a repeating orbit that looks like this, that has an ellipse. And the Earth in this case is at one of the foci, and there's nothing at the other foci. Okay? The other foci is, devoid of objects. The orbital center is always just at one of the foci by definition. So the speed of a satellite in an elliptical orbit does what? Okay? It varies. Okay? And that is distinct from a circular orbit, because in a circular orbit, the velocity was constantly changing. It's because it was always changing direction, but the speed was constant. That's what defines a circular orbit. In an elliptical orbit, both the velocity and speed are changing. The satellite is fastest here, when it's closest to Earth, and slowest when it's up here. And why is that? Well, it's all about energy. Okay, it's all about energy. Because up here, it's got big gravitational potential energy and small kinetic energy. Over here, it has small, okay, it's got, I'm going to make it smaller, smaller gravitational potential energy and big kinetic energy. Okay, but up here, the gravitational potential energy would be big. Okay, like that. All right, so it's just exchanging types of mechanical energy. Gravity for kinetic. All right. So there are some laws that apply to elliptical orbits. They were discovered some 500 years ago by an astronomer and scientist and mathematician, Kepler. So Kepler was an assistant to a famous astronomer called Tycho Brahe, who directed the world's first observatory. So then Kepler used data from his mentor Brahe to understand planetary motion, all right, and to figure out the motion of planets. And one of his discoveries was he found that planets were not circular, rather they were elliptical. This was a big breakthrough idea, because the whole motion of the heavens had been assumed to be perfect for a long time. That was just kind of part and parcel for what way people understood the world. We make assumptions, and we thought, oh, the heavens have to be perfect, right? They can't just be like Earth. But, they can't just be messy and follow the same sort of rules we see on Earth. But of course they do. Okay, the solar system is just as messy, complex, and chaotic as all the physical processes on Earth. And part of that story is elliptical orbits. Elliptical orbits of our own moon, elliptical orbits of planets around the sun. Okay, now some of those orbits are pretty close to circles, others not so much. All right, so Kepler came up with 3 laws of planetary motion. All right, you're responsible for these laws, but just remember that we got to this whole kind of side talk here about astronomy just by kind of following the threads of going projectiles to orbits, right? And this is just kind of a natural thing to relate. We're not going to make this an astronomy class or anything. We're just going to kind of discuss a couple of interesting laws that apply to really fast projectiles. Okay, so the first law: the path of each planet around the sun is an ellipse with the sun at one focus. All right, so you can see here's the sun at one of the foci. The second law: the line from the sun to any planet sweeps out equal areas of space in equal time intervals. All right, so in other words, to go from D to C takes an equal amount of time, so we call that time t, as to go from A to B. All right, equal time there as well. How do we know that it takes equal time to go from point D to point C along the elliptical path as to go from point A to point B along the elliptical path? Because these two shaded areas are the same, right? You've somehow measured those areas and you know that they're exactly the same, right? So what's that a restatement of? Well, that's just a restatement of conservation of mechanical energy. So Kepler's second law is actually conservation of mechanical energy, but it predates the conservation of mechanical energy as a law well known in physics. Okay, Kepler's second law came first historically. Now we know it by a different name, but they're consistent, the two ways to think about it. And finally, Kepler's third law says that the square of the orbital period of a planet is directly proportional to the cube of the average distance of the planet from the sun for all planets. Okay, so all that's saying is that the radius, which we'll say, kind of maybe a rough approximation for ellipse. So the radius squared is proportional or equal, if you use the right units, to the period, P for period, excuse me, P for period, cubed. Okay? All right, so, sorry about that. Miswrote it. So it's P squared, because it's the square of the orbital period, is proportional to the distance cubed. And actually here, instead of using R, I'll use A, because A is usually the letter that's used for the semi-major axis. And the semi-major axis is just going to be this distance. So this would be like A when the object is at point B, and then this would be A when the object is at point D. Okay, so A is just that semi-major axis. Okay, no, sort of. Okay, you can also divide up the cube into the cube. Excuse me. We can divide up the ellipse, and we can call A this distance here. It's probably better to call it that. Okay, but the point is, whatever is your distance from the sun, if you cube it, it's going to be equal to the square of the period. This is most helpful for just thinking about A as kind of the average distance, just to be a little bit rougher about it. So find the average distance of a planet like Jupiter, cube it, and then take the square root, and now you've got the length of the Jupiter year. So it's kind of neat because it can tell you exactly how long planets take, or if you know how long it takes a planet to go around the sun, then you can find its distance. So this is just pointing out that Kepler's laws are consistent with conservation laws we've already seen. So the object in motion possesses kinetic energy due to its motion. An object above Earth's surface possesses potential energy by virtue of its position. So a satellite in orbit possesses both kinetic and potential energies, and that sum must remain the same because we're assuming no change of energy to other forms like heat. All right, so here's the idea that the sum of potential and kinetic energy remain the same throughout a circular orbit. All right, and here this is a circular orbit. We've got the force of gravity shown here pointing inwards at any point, unchanging sum of potential and kinetic. And since it's circular, the potential actually never changes, and neither does the kinetic. So this is just everything remaining constant. Right? That's the nature of satellites. Okay, but in an elliptical orbit, well, like I sketched before, it varies. All right, this figure is better than my sketch on the previous slide, right? You can clearly see that when the satellite is far away from Earth, it's got big potential energy and small kinetic, and vice versa when it's close. All right. So when a satellite gains altitude and moves against the gravitational force, its speed and kinetic energy decrease, and the decrease continues to the apogee. The apogee is just the distance of greatest length away from the center of the planet. Past the apogee, the satellite moves in the same direction as the force component, and the speed and kinetic energy increase. The increase continues until past the perigee. That's the perigee is over here, which is the point of closest approach, and the cycle repeats. All right, so the whole purpose of this slide is to say that, yeah, you can just think of it as conservation of energy and just think about your distance and then say, oh, your kinetic energy must be less when the distance is greater, vice versa. Or you can actually think of it in terms of accelerations. So here, the direction of the force is actually creating an acceleration. The force is actually affecting this component of the velocity vector, right? That component that otherwise is unaffected, because that's the whole deal with projectile motion, right? So let's bring it back to projectile motion. We had that big assumption that the horizontal component was unchanging. That's true of circular motion of a satellite. We can actually use those same rules. The horizontal component, so we could think, the horizontal component of the velocity, let's call this v horizontal, is unaffected by the force because the force is always perpendicular to it. But the complicated but cool thing about elliptical orbits is that that's not the case anymore. Now the force, due to the shape of the ellipse, the force always points to the center of the planet, which means now the force can have components that do act along the tangential direction. This is the tangential direction, T, and components that act along the radial direction, R. We already would expect the force to act along the radial direction because it does it in a circle, and it does that for projectiles, acts down, right? But now the fact that the force also acts along the tangential direction means that the speed is non-constant. It's accelerating. There's acceleration in both directions, okay? Whether you call that the tangential and radial, or you call it X and Y, horizontal, vertical, whatever you name the axes, The fact of the matter is that for elliptical orbits, the force creates acceleration along both axes. Okay? Yeah, so it's a different story. Okay? So basically, we started with projectiles, went to satellites, then went to more realistic satellites that are elliptical, and realized that they're kind of not projectiles anymore because they have a force that acts along both axes. But they're still projectiles by that definition of saying that the only force is gravity. Okay, it's just that now the force is messy in that it's got a direction that's varying. Okay, now I hope that's interesting. Anyway, so let's wrap this up a little bit. Escape speed. So this is the idea that if a projectile is going fast enough, it actually doesn't even, because I mean, think about the cases, right? There was the speed to achieve, first of all, if you don't go fast enough, you crash back into Earth. That's just a long-range projectile, okay? That may be like an intercontinental ballistic missile, right? It can go really, really high, but eventually crash back down, okay? And then you got a satellite, so now you've gone fast enough, just fast enough that you got that perfect circle, okay? But then if you go even faster, if you quote-unquote overshoot your initial thrust velocity, then you end up with a elliptical orbit. But what if you go even faster? What if you make that ellipse more and more eccentric, more and more elongated? Well, eventually it sort of breaks open and it becomes a parabola. And once that velocity is just fast enough to turn the ellipse into a parabola, that's called escape speed. All right? And all the math here is conics, not that we're going to get into it, but it's all the math of what called conic sections, okay? And so now that's it. Now that's escape speed, turning what would have been an elliptical orbit into a parabolic path. I call it a parabolic path because it's not really an orbit anymore because you're never coming back. Now you've permanently left the influence of the gravity of Earth or whatever you started. All right? So when a projectile achieves escape speed from Earth, it, all right, I just said it, outruns the influence of Earth's gravity but is never beyond it, okay? Why is it never beyond it? Because the gravity never truly disappears. But there's enough kinetic energy that it will always have kinetic energy to never get pulled back, okay? So the voyages to the Moon, Mars, and beyond begin with launches that exceed escape velocities from Earth, okay? So there are cases where we have sent probes into space and given them enough initial velocity to escape Earth, okay? So it can go off and explore other planets or some even leave the edges of the solar system. All right. Well, I hope this has been an interesting discussion and like I said, our last one really covering motion. So as we move into other fields of physics. And thank you so much for watching. And I look forward to any questions and just further discussion on these topics.